Hello. For the past 2 months, I've been working on a passion project of mine, which is formalizing Chapter 1 of Michael Spivak's calculus textbook. That's his fourth edition textbook. I formalized the Chapter 1 exercises in a theorem prover called Coq. And so for anyone who's working on the exercises and struggling, or just for anyone who's interested in what formal solutions to simple problems in real analysis look like, I will leave the repository link in the video description. And for the rest of this video, I'm just going to cover one of the exercises that I really enjoyed, exercise 24. So with that being said, let's head to VS Code. Problem 24. This problem shows that the actual placement of parentheses in a sum is irrelevant. The proofs involve mathematical induction. If you are not familiar with such proofs but still want to tackle this problem, it can be saved until after Chapter 2, where proofs by induction are explained. Let us agree for definiteness that a1 plus ... plus an will denote a sum of this form, which is to say a sum with right associativity. Thus, and then there's some examples given of what right associativity looks like. And we want to prove that a1 plus ... plus ak plus 1 is equal to a1 all the way to ak plus 1 summed up, all with right associativity. So let's go ahead and prove that with the Coq theorem prover. So first I'll create a new file and I'll call it problem24.v. And the first thing we need to do is import some libraries. So we'll require import reals, which gives us access to the real numbers, and we'll need list. Okay. And with list, we will also import list notations. Now, when Spivak is talking about numbers, he's talking about real numbers typically. What we want to do is open scope our scope so that if we just type in a raw number, it'll be interpreted as a real number. So the first step is going to be to define this notion of sum that Spivak has with right associativity. And the way we're going to do that is with a recursive function, a fixed point. So we'll define a fixed point, and I'll call it standard sum. Which will take L, which is a list of real numbers, and it will return a real number. And the definition will be a match on the list L. Now, if we were adding up, if the list had no numbers and it was empty, then we would be adding up no numbers. So yeah, it would be 0 would be the result. If the list had a single element, then adding it up would just be x. And if it had a head and a tail, then it would be x plus standard sum of the tail. Let's do a reality check to make sure that this actually corresponds with Spivak's definition. So we can create an example, and I'll call it example 3 for the 3 elements we're going to sum up. And the statement of the example will be for all a, b, c belonging to real numbers. That's implied. Standard sum of a, b, c would equal a plus b plus c. Okay, let's intros ABC and go ahead and simplify. And sure enough, we can dispatch the goal of reflexivity. Now, what would happen if we had 4 numbers? A, B, C, and D. Then we would expect A plus B plus C plus D. And then we'll introduce them all. Simplify and reflexivity. Okay, so we have some idea that standard sum corresponds to Spivak's definition, but we can never know that by showing it on a finite number of instances. We would need to show an infinite number of instances, which is impossible. So what we'll do is utilize inductive thinking, which is to say, we know that our definition would work if the list was empty, if the list had 1 element, 2 elements, 3 elements, 4 elements. Suppose it worked for n elements, and show that it would work for n plus 1. So if it worked for n elements, then that would give us that standard sum sums them up in the correct order with right associativity. And if that's the case, would x plus standard sum of xs work? Yes, because standard sum of xs would be summed to the right, or with right associativity, and then x would be added to the left, and it would be added after all of these were summed up correctly. And so overall standard sum does correspond always to Spivik's definition. Let's go ahead and have a look at the lemma. Prove that when you do a sum of k, a standard sum on k integers, and then add a k plus 1 integer, it's equal to a standard sum of k plus 1 integers overall. So we're going to do a little bit of a different lemma, but it's still going to help us prove lemma B. And the reason it's going to be different is because in Calc, when you build a list, which we're going to do, you build a list from the front, not from the back. So our lemma is going to be lemma 1-24-A, and it's going to be for all L and A plus standard sum of L is equal to standard sum of A with L concatenated to the end. And actually, for a proof like this, we're not even going to need induction. So we'll introduce L and A into the context as variables, and we can destruct L as empty list or as a list A prime, as a list with A prime as the first element and L prime as the end. So first we'll do the case that L was empty, and we can just simplify and then apply R plus 0 on the right. Okay, and in this case, we can simplify, and then we can just call reflexivity. It's a bit of an eyesore, but if you look carefully, you'll see that the two expressions are the same. Okay, great. So we have our first lemma, and let's go ahead and check out what we should prove next. So we basically want to prove n greater than k, then a1 summed to ak in standard form, plus ak plus 1 all summed to an in standard form is equal to all of those n elements summed in standard form. So our translation of this proof would be lemma 1-24b. It would be that for all L1 and L2, which are lists of real numbers, and let's make sure we do it in the same order, it's summed separately equal to summed together. So standard sum of L1 plus standard sum of L2 is equal to standard sum of L1 concatenated to L2. Okay, we'll introduce L1 and L2 into the context, and it's going to be an inductive proof this time. So we'll do induction on L1, which will take A as a argument for the second constructor. We'll take L prime, L1 prime, I should say, and we'll get an induction hypothesis with that. So let's prove the base case with a simplification and apply R plus 0 on the left. Now we get access to the induction hypothesis. So the first thing I want to do is rewrite this expression . Oops. Must be that I have to Control C it. Okay. And instead of rewrite, I actually want replace with A prime concatenated to L1 prime plus L2. Okay, and we can do that with just simplification and then reflexivity. Okay, good. And now what we can do is actually apply our prior lemma. This is where this lemma comes in to assist us. And the reason is because the lemma basically states that if you have a standard sum of some element concatenated at the beginning of a list, and we see that here, and we see that here, then it could be rewritten to the left as stripping off the first element, then adding it to the standard sum. So we're going to repeat, because it can happen twice, and rewrite to the left, lemma 124a. Okay, and now we can utilize our induction hypothesis, which is to say anywhere we see this expression, which we see here, it could be rewritten to the left. So let's rewrite our induction hypothesis. And now we can simply call, or rather apply, R plus ASOC. And we have the lemma. Great, not so bad so far, but it's about to get a little more challenging because in lemma C, we have this definition S. Let S of A1 to AK be some sum formed from A1 to AK. So, the problem with this is that, with the prior definition, for instance, standard sum, it was a concrete, it produced a concrete result. This needs to produce a concrete result somehow, and it also needs to be able to represent every possible sum. So let's start with the representation of every possible sum, and it might not make sense at first that it works, but I'll go ahead and say some more about it to clarify it if needed. So we can define every possible sum with an inductive type in Coq. So let's define an inductive type, and we'll call it addition expression. An addition expression is a type. Now, what could an addition expression be? Well, it could be a number, which is a constructor, and the constructor holds A, which is a real number. And we don't need that. Okay, and what else could an addition expression be? Well, it could be a sum of E1 and E2, which are themselves addition expressions. Okay, so first things first, let's just understand how this can even represent anything at all. So if we just had a number like A, what would the only possible addition expression on A be? That would just be A. What if we had numbers A and B? Well, those could only be A plus B. And what if we had A, B, C? Well, that could be A plus B plus C. It could also be A plus B plus C. And let's just verify that our inductive type add expression can even represent those. So I'm going to create a section, and I'll call it local scope. And in this section, I'll define some variables. A, B, and C, which are real numbers. And now let's go ahead and just check num of A in add expression. So sure enough, we can represent every possible addition expression on a single element. Well, what about two elements? Well, that would be sum of num of A and num of B. So sure enough, and that's the only possible addition expression for 2, so we can do that. But what about for 3? Okay, so it could be two different ways. So it'll start with a sum, and it could be num of A, and then it could be sum of num of B, num of C, and the other way it could be is sum followed by another sum immediately thereafter of num of A, num of B, followed by num of C. So sure enough, it's powerful enough to be able to express every possible addition expression that contains one real number, two real numbers, or 3 real numbers. But what about 4? Well, let's find out. So we could have A, B, C, or D. Now the trick here is going to be the key insight is to recognize that given every addition expression, in the process of evaluating it, there must be a last addition. And let's think about why that's the case. That's the case because addition is a binary operation, which takes a number on the left and a number on the right, adds them together, and produces as a result one number. So we went from two numbers, performed an addition, and we ended up with one less number. And so if you're trying to add up, let's say, 4 numbers, you're going to do an addition, then you only have 3 numbers left. Another addition, then you only have 2 numbers left. And that would be true with 5, 6, 7. So eventually, as you continue to do an addition, you're going to be left with only 2 numbers, and you're going to add those together, and that would be your last addition. So every addition expression always has a last addition, and the only question is, where does that addition go? So in this case, A, B, C, D. Let's suppose the last addition occurred right here. Well, if that was the case, then we would have, every possible addition expression for A, which is just A, plus every possible addition expression for B, C, and D. So that could be B plus C plus D, or it could be A plus B plus C, and then plus D. Well, what if we cut it after B? Then it could only be A plus B plus C plus D. And suppose we cut it after C, then it could be everything on the left combined with everything on the right. So it could be A plus B plus C plus D, or it could be A plus B plus C plus D. And the key thing here is that we already established that our inductive type add expression is capable of representing every possible addition expression of size, for instance, in this case, 3. And so would it be possible for doing it for 4? Well, when we look here, suppose you cut it in between A and B, can our addition expression represent every addition expression that has 1 element? Yes. And then it would only have 3 on the right, and it could do that. Could it do for 2 on the left, 2 on the right? Yes, because we showed it could do 2. Could it do 3 on the left and 1 on the right? Yes. So now we know that it can do every addition expression of size 4. What about size 5? Well, again, with size 5, it will have every addition expression of size 5 will have a last addition. And so you just cut it at every place where the last addition could be, and then you always have at least a case which is smaller by at least 1. And so this is essentially inductive thinking. The fact that we can do it with 3 implies we can do it with 4. The fact we can do it with 4 implies we can do it with 5. The fact that we can do it with n implies we can do it with n plus 1. And so indeed, addition expression can represent every possible addition expression with n integer or with n real numbers. Okay, great. So now we've established that we're capable of expressing every addition expression of n real numbers, but this doesn't have a way to extract the result of the computation. It just represents the expression as a whole. So what we're going to do is create another fixed point, and we'll call it eval add expression. Now that's going to take an expression e belonging to add expression, and it's going to return, of course, a real number because it's going to sum them all up. And the definition will be a match on the expression. Now the expression could be a number, in which case just give me a, or it could be a sum of e1 and e2. And if that was the case, just evaluate e1 and then add the result of that evaluation to evaluation of e2. And again, we apply inductive thinking the same way we applied it with standard sum to recognize that this will always produce the correct result. Okay, so we're almost there. We can almost begin to prove lemma C, but there's one more thing we need, which is if we look at the lemma, we're trying to show that if we have an addition expression, s of a1 to ak, it would be the same if you took all the real numbers out of the addition expression and then summed them up using standard sum. But the problem is we're going to be given in this lemma an arbitrary expression, but we don't have the list of real numbers from that expression so that we can perform the standard sum on it, because standard sum takes a list of real numbers. So we're going to need to define one last fixed point, and I'll call the fixed point elements. which takes an expression E belonging to add expression and is going to give us a list of real numbers. And it's going to be, again, a match on E. And if E was just num of A, then just give me a list A. And if it was sum of E1, E2, then just give me elements, elements of E1, which is a list of real numbers, concatenated to elements of E2. And again, using inductive thinking will give us that this function is always correct. Okay, so let's go ahead and prove the lemma now and just look at it to make sure. So we're given some arbitrary addition expression. We're going to evaluate it, and we want to know that the result is always going to be the same as if we had applied standard sum on the elements of that arbitrary expression. So let's go ahead and state that and prove it. We want lemma 3, lemma 1, 24, and I believe I'm calling it A, B, C. C. So for all E, which are addition expressions, eval add expression of E is equal to standard sum of elements of E. Okay, let's prove this. Let's introduce E as a variable in the context, and it's going to be an inductive proof, so we'll do induction on E. Now, when you do induction on E, we need to pass arguments to all the constructors. The first constructor takes A as an argument, and the second constructor takes expression E1, and we'll get an induction hypothesis for that, so we'll call it induction hypothesis 1, and argument E2, and also we get an induction hypothesis for that, and we'll call it induction hypothesis 2. Oh, and I need the keyword as. Okay, so let's just simplify, and we get reflexivity. And we'll simplify again. Okay, now is where we can use lemma 124b. And if we look right here, we have standard sum of two lists concatenated together is equal to the standard sum of the lists separately added. And we have standard sum of two lists here because elements of E1 gives a list and elements of E2 gives a list. So let's go ahead and rewrite lemma 124b to the left. Rewrite lemma 1-24-b. Okay, excellent. And now, let's see, simplification does nothing. Yes, now I believe is the time to apply our induction hypothesis. So we see eval add expression E1, and we have that here, and eval add expression E2, and we have that here. So let's simply rewrite IH1, rewrite IH2, and now I believe we simply have reflexivity and QED. Okay, so that's where Spivak ends the exercise. But believe it or not, it doesn't actually quite prove what he wanted to prove, which was ultimately that the actual placement of the parentheses in a sum is irrelevant. And the reason he basically stopped at C is because there's such a small amount of logic required to go from C to the proof of the statement we actually wanted that he basically figured anyone can see it in their heads instantly. But if it really was that simple, we should be able to prove it, and it really shouldn't be that difficult. So let's go ahead and prove it anyway. And to really complete the proof of what Spivak wanted to show, we would need to, let's define a new lemma, and we'll call it R plus ASOC general, which is to say for any number of elements, associativity on addition on real numbers holds. And that is to say, if we're given two expressions, expression 1 and expression 2, and it happened to be that they were parenthesizations of the same list of numbers. So that is to say, elements of E1 would be equal to elements of E2. If this is the case, then when you evaluate E1, it's going to be the same as an evaluation of E2. Okay, so let's intros E1, E2. And also we want to introduce a hypothesis. And now what we can do is, I believe, apply lemma 124c, which is to say, if you're evaluating an expression, it's equal to the standard sum of the elements of E. And we want to do that for both of our expressions, so let's rewrite twice, or rather repeat repeat, rewrite lemma 1, 24C. And now we can rewrite the hypothesis. And we have reflexivity.